Welcome to today's Explainer. We're unpacking a really fascinating David and Goliath scenario in the world of physics. We're going to put the most successful framework in history, the Standard Model, head-to-head against a highly disruptive new theory called the Pendulum Big Bang atomic model. So, if you've ever found yourself wondering whether the universe is actually built on elegant, tangible geometry rather than just incredibly complex statistics, well, you're in exactly the right place. Let's dive in. We've got a clear roadmap to tackle this today. First, we'll look at the Standard Model's limits. Then, we'll explore the Pendulum Big Bang. Third, rethinking Heisenberg's uncertainty. Fourth, Dirac quaternions explained. And finally, number 5, testing a unified framework. All right, let's jump straight into Section 1, the Standard Model's limits, the confinement problem. You know, our current understanding of protons and neutrons relies heavily on what the source material calls the watermelon seed analogy. Basically, in the Standard Model, quarks are viewed sort of like seeds trapped inside a watermelon, and they're held together by particles literally called gluons. But here's the kicker. We have never, ever actually seen a free gluon or a free quark. Because of this phenomenon we call color confinement, the math of quantum chromodynamics, or QCD, has to rely on insanely complex simulations just to make it all work. Sure, it functions mathematically, but man, it is remarkably difficult to visualize physically. And the contrast between these two frameworks is honestly striking. The Standard Model leans entirely on this unobserved glue and sheer statistical probabilities to bind the nucleus together. But Dr. Ahmad Rihan's pendulum model, it actually throws away the mysterious glue entirely. Instead, it proposes these perpendicular triple-quark bodies. In this model, confinement isn't some added force you have to plug into an equation. It's just a natural, inescapable feature of the mechanical geometry itself. So, hearing that, you've naturally got to wonder, how exactly does this new geometric architecture actually form from scratch? That brings us right into Section 2, the Pendulum Big Bang, a new genesis. Okay, so forget the traditional idea of a singular point of infinite density. This alternative model starts with a dynamic, divided origin. Picture a primordial energy cloud cleanly splitting into 4 equal parts. Then, these 4 parts undergo this simultaneous, interpenetrating collapse. Because they crash into each other and pass right through, they spark a massive pendulum-like oscillation. And this is where the physics gets really incredible. This vibration literally quantizes the energy. The energy condenses first into baseline units called egyptons, which then form threads and finally create quarks, assembling into a highly structured mechanical universe built of those perpendicular triple-quark bodies we just talked about. Now, as these particles form, they layer themselves using what the model calls Faraday quarters. Driven mathematically by Euler's formula, these very specific geometric rotations dictate exactly how successive layers of the nucleus orient themselves, moving from the neutron layer to the proton layer all the way out to the antineutrino layer. And this mathematically driven geometric rotation perfectly explains a massive real-world mystery: why the nucleus is packed so unbelievably tightly, especially when you compare it to the giant empty void that exists right before you hit the electron shells. Now, it's one thing to draw a neat geometric picture, right? But physics has incredibly strict rules. That brings us to a critical theoretical hurdle and forces us to look at how both of these models deal with the undeniable, chaotic reality of quantum uncertainty. Let's get into Section 3, Rethinking Heisenberg's Uncertainty, Geometry versus Statistics. Currently, the Standard Model doesn't really offer a physical, geometric reason for Heisenberg's uncertainty principle. When you're dealing with the incredibly tight confines of a nucleus, the model relies on things like gluon flux tubes and some seriously dense math known as non-perturbative QCD. And because that math is so tangled, mapping exact wave functions for these internal structures is, practically speaking, analytically impossible. Now, don't get me wrong, it works beautifully as a statistical model for predicting outcomes, but it totally leaves us in the dark about why this uncertainty actually exists in physical 3D space. The Challenger model, however, takes a completely different approach. It bakes uncertainty right into the physical geometry. Remember those triple-quark bodies? Well, their centers actually perform these rapid up-down circle dances. Because the particle is physically vibrating like that, you simply can't pin it down. And boom, you have geometric uncertainty. This physical oscillation inherently imposes a natural spread in position, and amazingly, it even manifests as effective mass, completely bypassing the need for an external Higgs field. On top of that, opposing circular and perpendicular movements perfectly cancel local forces out, maintaining what the paper calls mandatory equilibrium. So we have this really beautiful mechanical explanation for uncertainty. But visual analogies are only helpful up to a point, right? At the end of the day, physics requires rigorous math. So let's see how this visual model maps onto established algebraic frameworks. Moving on to Section 4, Dirac quaternions explained. Mapping the math. The paper boasts an absolutely incredible one-to-one mapping with Dirac's quaternion mathematics, which is a system used for encoding four-component spinors. The physical geometry translates flawlessly to the algebra. Check this out. The four particle types map perfectly to the base quaternion units. The opposing orbits become mathematical conjugates. Those perpendicular quark leaflets, they act as spatial imaginary axes. The central physical oscillation operates perfectly as the mass term in the equation. And those Faraday quarter rotations serve as the multiplications driving the wave function evolution. It's a really striking translation of physical space directly into mathematical certainty. So why does this specific mathematical debate actually matter for us? Well, because while the standard model's complex 4x4 gamma matrices operating in Minkowski space are absolutely robust and they do work, they're also highly abstract. The pendulum model argues that by embedding quaternions right into the foundational geometry, we get back a spatial intuition that is currently completely missing from modern physics. It literally makes the mathematical workings of the universe easier to picture in your head. Which brings us to our final stop, Section 5, Testing a Unified Framework. The verdict. The overarching claim of this paper is that the pendulum model gives us much deeper why explanations. It dynamically derives confinement, mass, and even space-time itself straight from physical geometry, rather than just mathematically inserting them the way the standard model often has to. By requiring way fewer ad hoc parameters, claiming to totally avoid the dreaded hierarchy problem through natural amplitude tuning, and even offering a pathway to integrate gravity through that global mandatory equilibrium, it represents a seriously bold, sweeping attempt at total physics unification. But let's be real. Elegant ideas mean absolutely nothing without testable predictions. Ultimately, the paper calls for rigorous simulations and high-precision spectroscopic testing. They want to hunt for the specific multi-Gaussian spectral signatures and density effects predicted by this exact model. If those layer-specific transitions are ever verified in a lab, it would completely validate this pendulum-driven cosmos. And it leaves us with a really profound question to chew on. Are we about to trade our statistical universe for a purely mechanical one? Thanks for joining me on this explainer, and as always, keep questioning reality.